Welcome to section 3.3. These are establishing and using different identities. And then a few other things that are involved here. Example number 1 says to rewrite in terms of sine and cosine, and that would be the cotangent of x times the tangent of x. And we use the reciprocal identities. Cotangent of x means or is equivalent to the cosine of x over the sine of x, and the tangent of x is sine of x over cosine of x. And when we look at this, it does simplify to a very simple 1. Example number 2 says factor and simplify. And here we need to understand or to realize that functions, trigonometric functions, can be treated just like any other variable. And so whenever you have this example 2 sine squared of theta plus 3 sine theta plus 1, really what is happening, this is the equivalent of 2x squared plus 3x plus 1, and just like sine squared of theta minus 1 is x squared minus 1. And so what we can do is we can factor each and every one of these. If we factor the numerator, this becomes 2 sine of theta plus 1 times sine of theta plus 1. And the denominator can be factored. That's the difference of squares. So that will be the sine of theta plus 1 times the sine of theta minus 1. And notice the sine of theta plus 1 in both the numerator and the denominator will cancel each other out. And so that leaves 2 sine of theta plus 1 all over the sine of theta minus 1. And that becomes the final answer. Example number 3, actually 3 through 16, the rest of this particular section deals with establishing identities. And so the first one is cotangent of of theta times the secant of theta. We need to somehow prove that that equals the cosecant of theta. Now whenever we are dealing with establishing identities, what we need to do is we need to choose the most complicated side and work with that one until we get to the simpler side. And there are many ways to do the same thing, but basically I'm going to look at reciprocal identities here. Cotangent of theta is equivalent to the cosine of theta over sine of theta, and secant of theta is equivalent to 1 over the cosine of theta. Well, it's very easy to see that the cosines of theta will cancel each other out, and we're left with 1 over the sine of theta, but the 1 over sine of theta does equal cosecant of theta using the reciprocal identities. One thing that's very important when you're establishing these, you need to show step by step. What are you doing? In this step, I'm just rewriting it using the reciprocal identities. Next step, I simplified, and then this is using a reciprocal identity to get there. Example number 4, cosecant squared of u minus cosine of u secant of u equals cotangent squared of u. Now, anytime I see a squared, that's probably going to tell me I'm going to want to deal with a Pythagorean identity. And so in this case, I'm going to take cosecant squared of u and rewrite that as cotangent squared of u plus 1, as allowed for in the identity. Then the next step that I'm going to do, I'm going to realize, okay, secant of u is equal to 1 over cosine u, and look what happens there. So we get cotangent squared of u plus 1 minus the cosine of u, and secant is 1 over cosine of u, and look what happens there. So we get that. We get cotangent squared of u plus 1 minus 1 equals cotangent squared of u, and we are finally to where we need to be, and so I put the 3 points there, which simply means I've proven what I needed to prove. Hopefully I'll have enough room here. Example number 5 is the secant of u minus the tangent of u, that quantity, times the quantity secant of u plus tangent of u, and that all better equal 1. Well, obviously this is the more complex side, so what I'm going to do, I'm going to look at that and say, hey, this is a difference of squares, so I'm going to go ahead and multiply them together and get secant squared u minus tangent squared u. And let's see what I get from here. Well, I'm seeing squareds, so squareds usually tell me Pythagorean identity. Secant squared of u can be written as tangent squared of u plus 1, and then we still have that minus tangent squared of u. But very easily, tangent squared of u plus 1 minus tangent squared of u equals 1, which is exactly what we wanted it to equal, and so we are ready, or we have proven what we needed to prove. Example 6. The tangent of u minus 1 over tangent of u plus 1 equals 1 minus cotangent of u over 1 plus cotangent of u. And what we're doing here is we are going to take this whole thing. Now, anytime we have fractions like this and we're trying to show that it's a fraction, generally speaking, here we could argue, certainly, that any one of these two are equally complicated. And so what I'm going to suggest is that we just pick one of them. And in fact, I'm going to take this left-hand side. And what I'm going to do is I'm going to divide both the numerator and the denominator by the tangent of u. As long as we divide both the numerator and the denominator by the same thing, then we're perfectly fine. Now I look at this and I can give this tangent of u to both of them. So tangent of u over tangent over u of u is 1 minus 1 over the tangent of u. Likewise, I can do the same thing for the denominator. Tangent of u over tangent of u is 1 plus 1 over tangent of u. And then 1 over tangent of u is the cotangent of u, and 1 over tangent of u here is the same thing as 1 plus cotangent of u, which is exactly what we needed. Number 7. Secant of theta minus 1 over the tangent of theta is equal to the tangent of theta over the secant theta plus 1. Once again, it's arguably just as difficult both ways. So I'm going to start with this left-hand side, and what I'm going to do is I'm going to multiply both the numerator and the denominator by the same thing, secant of theta plus 1. Just like in example 6, I divided by the same thing, you can multiply by the same thing as well. So I'm going to take secant of theta minus 1 and multiply by secant of theta plus 1. And notice there is a reason why I chose that, because now this gives me a perfect square, and perfect squares usually mean Pythagorean identity, and we can work with that. But then we need to remember to take the tangent of theta times the secant of theta plus 1 as well. Now what happens to the numerator is we get secant squared theta minus 1 over tangent theta secant theta plus tangent theta. Now, secant squared theta minus 1, I believe, is equal to the tangent squared of theta. And I realize I made a mistake up here. I probably didn't want to distribute this, so I'm going to factor it back out. And notice what happens here. We have a tangent squared of theta and tangent of theta here. I can cancel out the squared there, which will take care of that, and we're left with tangent of theta over the secant of theta plus 1, which is exactly what we wanted. And finally, number 8, cosine of u over 1 plus tangent of u minus the sine of u over 1 plus cotangent of u. We need to show that that equals the cosine of u minus the sine of u. Now one thing I'm going to look at here is I see cosine and sine as the simple, so that might mean, hey, I want to change everything in terms of sines and cosines. So I get cosine of u over 1 plus the sine of u over cosine of u minus, and do the same thing here, the sine of u over 1 plus cosine of u over sine of u. Now this will equal, okay, the denominator, we need to get a common denominator, so that will be cosine of u over cosine of u plus sine of u all over cosine of u minus, same thing, finding the common denominator of sine of u down here will give us sine of u plus cosine of u all over sine of u, and that we still need that sine of u that was way up here. Okay, so simplifying this becomes cosine squared of u, cosine u plus sine u, minus sine squared of u, sine u plus cosine u. And realize these are the same denominator, so we should be able to combine these. And realize we will have cosine squared minus sine squared. Well, that's a perfect square, so I'm going to factor that out. So I get cosine of u plus sine of u times cosine u minus sine u all over sine u plus cosine u. And notice this factor will cancel with that factor, leaving the cosine of u minus the sine of u, which is exactly what we wanted.